name is Marv Anderson. I'm from Iowa State University, Ames Laboratory, which is operated for the Department of Energy by Iowa State University. I'm the project coordinator for this mobile laboratory. What you're in here is a 27-foot long by 8-foot wide by 7.5-foot high laboratory. This is the working intelligence center for the instrumentation that we have installed, which uses inductively coupled plasma coupled with a atomic emission spectrometer to do in situ soil sampling. On the desk here we have a 8-pin plotter and a printer for results. With the plotter, once we have developed the sampling scheme and the amount of contamination, we can contour on the site so that we can give you a real-time map of our results. We have a printer so that we can print out the results. What we have here are the control center for the instrumentation. We have 3 computers. The first 3 computers are dedicated to controlling all of the gas flows, temperature, any instrumentation information that we have to monitor and change while we're in the process of sampling. The 4th computer is dedicated to the spectrometer, where we take the data and the spectrum shows up on there, which gives us our contamination levels. We have a black and white TV camera monitor here, which allows us to look at the sampling site while we're sampling. Okay, in the rear end of the laboratory here, we have all of our instrumentation. We have our 4 computers and the UPS system. Behind me is a T. Gerald Ash ICAP 61E spectrometer. It's an off-the-shelf purchased item. We have set it in a special vibration mount so that we can use it in the field. The spectrometer, we have a Continuum 81 Series E neodymium YAG laser. This laser is a high-powered laser. We use the doubled frequency of 532 nanometers. This instrument, we focus into the end of a fiber. We send the signal, the energy out to the soil where we actually do the ablation. This is our sampling technique. The spectrometer that I referred to earlier is the device which does the analysis of the sample. We have our power supplies to operate both the spectrometer and the laser. In this side we have an instrument water chiller, which is used to chill the water for the instruments. The instruments, for cooling purposes, need chill water. On this side we have a small half-meter spectrometer, Acton spectrometer, and the control is on the back desk here. What we have here is an important device which is connected with this laboratory. This is the end effector. This is very important because this is the device that does our in situ sampling. In this box we have 3 stepper motor operated optical tables. We have an X and a Y to give us the rastering for our laser beam and a Z to do the focusing. Also in this box is the water, which does the sealing to the soil. In order to take a sample, we actually put argon gas into the ablation chamber and sweep the particles down a tube back to the robotic trailer in the back. The sampling system focuses a laser onto the soil, which does the ablation, and it uses a few tens of micrograms of particles that it puts into the airstream for analysis. The ablated particles come down this umbilical and are brought into this RSA, robotic sampling accessory, and they are burned in this remote ICP. There's a flame in here that is an argon plasma. It turns out that the flame is running at about 8,000 degrees Kelvin. As these particles are injected into this flame, they're atomically and ionically excited, which gives up their fingerprint of what they are. A picture is taken of this flame. It's focused onto an optical fiber bundle, and it is taken into the spectrometer where it's analyzed. In the analysis, we learn both quantitative and qualitative information from this. The wavelength from the element is the qualitative, The quantitative is the intensity, and it's the intensity that we standardize or we calibrate to determine how much of the sample that or how much of the element is actually in the sample. This is an example of the ablation at a sampling site. The ring you see is caused by laser shots, and there's a lot of little dots that are side by side, 600 microns in diameter, that make up that ring. And this is actually a sampling site, and this is the result of ablation. The ablation site, the actual depth is about 100 microns is our penetration level, so we are a very surface-sensitive sampling technique. This is the wet chemistry area of this laboratory. In here we can prepare samples by microwave dissolution. We have a microwave oven here. We can hand grind them. We have a scale that we put in here. We can weigh samples, microwave dissolve them, and then feed them through a microtube into the spectrometer that's sitting in the main laboratory. This allows us to do direct chemical checks on these samples with the spectrum of what we expect from the ablated samples. Along with these laboratories, you need to think of safety. We have a eye wash device here because we do use acids in this area. We bring our own distilled water in a carboy. We do have a sink here with potable water in it for washing glassware when we've completed our sampling. One of the utilities that's of importance in this lab is the air conditioner. We need both to dehumidify the air and to keep the lab space cool so the instrumentation operates properly. We installed a 4-ton computer room type air conditioner in this space, and this is a unique use of this type of air conditioner. People usually don't put them in the mobile configuration, but we needed a device that would dehumidify in addition to reheat and cool the laboratory space. Another utility that's of prime importance when you're designing a mobile lab is the electrical power